Hey now, Petey Grizz here from PFG Pedals. And today, in this video, I'm going to continue with part 2 of my Fuzz Face mod series. In the first part, we went over the benefits of reducing C1, or the DC blocking cap at the input, and adding a cleanup pot or trimmer, variable resistor, to the input to shape the tone. And those are two of the most effective mods for Fuzz Face as far as yielding a wider variety of tone from the pedals. Next, I want to discuss this section, the feedback network and gain control. This is known as a shunt series feedback setup. This creates what's called a negative feedback loop, and the reason that is that the Fuzz Face utilizes what is called a common emitter amplifier scheme, and the effect of a common emitter amplifier is that when you take the signal off of the collector, it's out of phase 180 degrees from the input. Now, when we take that same signal that's now 180 degrees out of phase and go into Q2 and come out of its collector, it gets flipped again and ends up being back in phase with the input. Of course, the amplitude and waveform will be very different. But we don't just take the output from the collectors, we take the output from the emitter. When you take the output from the emitter of a BJT, it's called an emitter amplifier, or not emitter follower, sorry. While a common emitter amplifier amplifies and also inverts, the emitter follower does not amplify, or it has unity gain technically, which means it's not really amplifying, but kind of, and it's non-inverted from the input of that transistor, which means the signal coming out of this emitter looks just like the signal coming out of the collector here, although obviously the waveform and stuff might be slightly different. But what's cool about that is when you bring that inverted signal and bring it all the way back to the input of Q1 right here through R4 on my schematic. Mind you, other schematics might have a different numbering scheme, but the 100K resistor is pretty easy since it's the only 100K resistor. And by taking some of the inverted signal and blending it, or not inverted, out of phase. I keep saying, I had to redo this video because I kept saying inverted. Inverted is usually has to do with converting DC to AC. Here we're talking out of phase. So this out of phase signal comes back and blends with the in phase signal from the input. And when two signals are out of phase, they cancel out. Effectively, if you had two identical signals and you put one of them out of phase and then sum them together, you would have no sound. They would cancel out till there's just nothing audible. Since there's this resistance here, and also because these are not perfectly, mirror copies of each other, it doesn't cancel out the full signal. It cancels out a portion of it. What that does is reduces the overall gain of Q1, and just as importantly, it affects the overall stability and tone of the circuit by helping the circuit not go into like oscillations and noises from being at such a ridiculously high gain. Okay, ways to modify this are real simple. If this signal cancels out, then more signal will create more cancellation or less gain. Meanwhile, less signal will create less cancel or more gain. So we have the effect of raising the value of this resistor raises the gain of Q1, and vice, obviously then lowering it lowers the gain. So I've had success with values between 47 to 120K. 47Ks were seen in like I think in like the Vox distortion booster, like the Italian made Vox 2 transistor fuzzes, some other ones, but like the Dunlop JHF1, the Jimi Hendrix signature fuzz face, uses an 82.5K resistor there. So I find the sweet spot is between like 75 and 100K, but I've had success with as low as 47K and as high as 120K. Usually, if I'm dealing with really higher gain than ideal transistors, I'll lower this value a bit. And likewise, if I have especially with like the BC183s I have, they're kind of a lower gain silicon transistor, and so I raise the value, especially typically I use a 110 or 120 with them to give a little less feedback and a little more gain. If you go too high or too low, there will be negative. You'll get to a point where the circuit either doesn't work or creates noise. So there's a range that's ideal. Another part of that system is the fuzz pot. Since the fuzz pot goes to ground and is a lower resistance, a lot of this signal is just being sent to ground, okay? So the fuzz pot adjusts how much of that signal either goes to the feedback loop or is bypassed to ground through this capacitor. Now, for the AC signals concerned, basically, it's when you have the fuzz pot all the way up, the bypass cap is basically connected right here instead of here. So you can see that you've got it basically connected directly to the emitter. Changing the value of this is not really necessary. You can use a 2K pot. Some guys say a 2K pot is a little quieter. It sounds fine to me. It's not a drastic change. Another thing you'll see in some of the Vox, 2 transistor fuzzes, is a second resistor down here. So of a 1K linear pot and then a 1K resistor between the pot and ground. And sorry, this is a little sloppy. I drew it on in my first attempt at this video and didn't feel like doing it right. And yeah, that will it puts a little more resistance on the emitter, and it just quiets it down slightly. My favorite mod, and I don't even consider this is just how I build my pedals 99% of the time, is I use a reverse logarithmic taper. Now the standard scheme uses a 1K linear pot. When we talk about tapers, real quick, let me go over to this piece of paper. I drew them out already for my earlier version of this video. I guess I could have stopped and drew them better, but this is good enough. So looking at what a linear taper means, that means if here is the rotation and here is the resistance, whoops, it means that as you turn the pot up, the resistance climbs in a linear fashion. Basically, it's even. Ideally, of course, in the real world, these parts aren't perfect, but the ideal part would look like a straight line from 0 to 100 diagonally across this graph. Now, a normal audio pot, also called logarithmic, has imagine that, a logarithmic taper. And let me get an eraser real quick because this line screwed me up here. This line wasn't supposed to be there. Okay. Now, so an audio taper or logarithmic taper pot goes very gently for the most of the resistance, and then as you get closer to the end, the resistance ramps up faster. And this has to do with the way we hear things. If you use a linear pot in the volume, it tends to sound like it jumps up real quick, and then it doesn't seem to get that. Once you get to, like, say, 70% of the rotation, it doesn't seem to get that louder. It's because of the way our hearing is. Our hearing is not doesn't hear in a linear fashion. We don't perceive volume in a linear fashion. So that's why we use audio taper pots for volume controls. Now, the opposite of an audio or logarithmic taper is an anti-logarithmic or reverse audio. And the reverse audio does the opposite. The resistance climbs rapidly for the first, 50% or so of the rotation, and then the last bit goes very gradually. And what that means is if you look from here to here, that's the same amount of resistance as here to here on this pot. And what that means is you've got a wider range to dial in a sweet spot. And the fuzz face has a sweet spot. Generally, the fuzz face works best almost, you crank it all the way up and then you back it down till it stops being noisy. And that's as simple as it gets. And usually it's somewhere around 90%, like 5 o'clock or something like that. By using an anti-log pot, we're spreading that out. So now this same amount of rotation, the same amount of resistance is now spread out to, say, here on the pot. So you've got all this rotation, and it makes it very easy to find that sweet spot, because the tiniest move, sometimes with a linear pot, the smallest adjustment, it'll be like you adjust it and it's too noisy, and then you adjust it back and it's not gainy enough, and it can be very sensitive in some pedals. So using an anti-log reverse audio pot for the fuzz pot is highly recommended. Boom. Now, one more thing I'm going to talk about in this video is the output section over here. Now, the DC blocking cap at the output, much like C1, C3 over here, has some tone shaping characteristics, as well as serving the function of making sure the DC doesn't go into the next part in the chain. The thing is, it has the same relationship as the input cap, meaning that a larger value will let more bass through. Pardon me, smaller value will let less bass through. The difference with the output cap versus the input is the output is not as drastic. There's already a lot of filtering and stuff going on here in the circuit overall, like just by the nature of the circuit and the frequency response and such. So this, I find, doesn't make a huge difference, but it does make a difference. And I recommend experimenting with values between 4.7 nanofarad at the smallest, or 0.0047 to 0.1. So 4.7 NF to 100 NF. Most of the time, my favorite values here are the 10 nanofarad or 22 nanofarads. But I've had good results with everything in this range. Then we come on to the volume pot. And the volume pot has some tricks too. Now, the standard value is 500K. It used to be 470. But that's not a common value today. That's what they used back in the 60s. The difference between 500K and 470 is minimal. And frankly, when you take in consideration the tolerance, a 500 could easily be 470 or maybe 530K or more or less even. So, because these aren't perfect parts, as I said earlier. Now, the mod here is to change the value of this pot, and it's always going to be an audio taper. I mean, you can use linear, but this is not a big deal. I would go with an audio. Lowering this resistance value has the effect of changing the sound in that it makes it seem brighter. So the lower the value, the brighter it will seem. I believe this has to do with the way this works with this cap as a filter. But regardless of why, I know it sounds good. I have found the sweet spot to be 250K audio. But from what I understand and read online, Eric Johnson likes a 100K And some people like that. Some of the tone benders have that. Remember, your tone benders and fuzz faces are very similar circuits, right? Like, so a lot of the stuff that applies to one will apply to the other, even if it's a 3 transistor versus a 2 transistor. So I like the 250K audio pot here. I think that's the sweet spot. It doesn't sound too fat or thin. It's just got a nice full sound with enough brightness up top. You can always roll your treble off a little bit, but it gives you a little brighter sound, and I like it. So I think that's where we're going to call it today. We're already at 15 minutes. In the next video, I'm going to discuss messing with these resistors up here to get more output volume, and then also we'll talk about doing bias mods, like an external bias pot. Anyway, thanks for watching. I'll see you in the next one. Peter Grizz out.